Next question. Figure 4 shows the apparatus used to obtain the data needed to calculate the resistance of a thermistor at different temperatures. What we've got? Thermistor in, some water, thermometer in there, we've got our ammeter and our voltmeter. Voltmeters across the ammeter. Got a little Bunsen burner there in order to change the temperature of the water, I guess. In the box below, draw the circuit symbol for a thermistor. It starts off in life just as a normal resistor, and then it's got a sort of golf club coming through it. Use the data given in figure 4 to calculate the resistance of the thermistor at 20 degrees. So we're looking for resistance. It gave us voltage and current. So remember, voltage equals current times by resistance. That's our Ohm's law. So therefore resistance is going to be the voltage over the current. Voltage was 9 volts and the current was 0.025 amps. And that comes out as 360 ohms. Figure 5 shows the axes for a sketch graph. Complete figure 5 to show how the resistance of the thermistor will change as the temperature of the thermistor increases from 20 to 100. So temperature in degrees, say if we just sketching it out, so say 0, 20 degrees, 40 degrees, 60 degrees, 80 degrees, 100 degrees. And we're not really bothered about what the exact resistance would be. But if this is at 20, it does actually show us that at 20 degrees, that's what the voltage and the current is. And we've worked out that that was 360 degrees, 360 ohms, sorry. So we could actually sketch that on. So at 20, if we go up to say 400, so 0, 100, 200, 300, 400. At 20, it's going to be about 360. They're only looking for a sketch, so it's just rough. Now, what we know about a thermistor is as the temperature increases, we know that the resistance decreases. So at these higher temperatures, the resistance isn't going to be big still. The resistance is going to get smaller. And what we also know is it's not directly proportional. It's what we call exponential. So it's going to be a curve that goes like that. That kind of curve where it starts off high and comes down curved like that and never actually touches this 0 line, but just sort of comes along here like that. That's what we call an exponential graph. Which one of the following is most likely to include a thermistor? Tick a box. An automatic circuit to switch a plant watering system on or off. Oh, I wouldn't have thought so. An automatic circuit to switch an outside light on or off when it gets dark. No, that would be an LDR, light dependent resistor would need for that. An automatic circuit to switch a heating system on and off. Yep, anything to do with temperature. That is your thermistor's job. So it'll be that one. The ammeter used in the circuit has a very low resistance. Why is it important that ammeters have a very low resistance? Well, ask yourself, what do you want an ammeter to do? You want it to measure current. Now, what does resistance do? Well, it controls the size of the current. So it's no good putting an ammeter in if the ammeter's got a high resistance and it actually changes the current that you're trying to measure. So we need the ammeter to have a small resistance so that it does not affect the current when it is measuring it. Next bit. Table 2 gives the temperature of boiling water using 3 different temperature scales. Temperature 100, 212 and 80. Scale Celsius, Fahrenheit and Brummer. Scientists in different countries use the same temperature scale to measure temperature. Suggest one advantage of doing this? Well, so you can easily compare your results. I mean, if these are all the same temperature, well, that one's 100, that's 212, and that's 80. So it's not easy to say straight away what's what, is it? So if everybody just said, look, we're all going to use Celsius, then it would be a lot easier to compare and to share your results with other countries. A student plans to investigate how the resistance of a light-dependent resistor changes with light intensity. The student starts with the apparatus shown in figure 4, but makes 3 changes to the apparatus. One of the changes the student makes is to replace the thermistor with an LDR. Describe what other changes the student should make to the apparatus. So, a student plans to investigate how the resistance of a light-dependent resistor changes with light intensity. So if this is the circuit they're using, what they've said is they're obviously going to change the thermistor for an LDR, so we can't talk about that. Right, well, if we're going to measure the light intensity, we'd better take the thermometer out, because we don't need to measure the temperature, but we'd better put some kind of light intensity meter in. And instead of changing the temperature using a Bunsen burner, we could use a light bulb that would change the light intensity. And we might want to have a ruler so that we could have the light at various distances, and that would help us to change the light intensity. But it's only worth 2 marks, so the 2 that I think I'll go for is change the thermometer for a light intensity meter and change the Bunsen burner for a lamp. Next question. Figure 8 shows an electric drill. Right, let's have a look at it. Plastic grip, plastic cover, plastic handle, 2-core cable. Well, everything's plastic. The information in the box is taken from the booklet supplied with the drill. This drill is fitted with a 2-core cable. Right, so we don't need 3, we only need 2. And that's because everything's plastic. The cable that'll be missing is the earth cable. Power supply is 230 volts, 50 hertz. Power input is 1012 watts, and the mass of the thing 6 kilograms. Why is it safe for this drill to be fitted with a 2-core cable rather than a 3-core cable? So the missing cable is the earth. We don't need it because it's double insulated, which means none of the casing is actually metal, so none of it can become live in the event of the live wire becoming loose and touching the outer part of the drill. Basically, you'll get 1 mark for just saying it's double insulated. If the question was worth 2 or 3 marks, I've wrote an answer there that would allow you to actually get 2 or 3 marks. Calculate the current drawn from the mains, so current, I is question mark. Calculate the current drawn from the mains electricity supplied by the drill. Use the correct equation. So what have we got? We've got the voltage and we've got the power. Okay, so power equals current times by voltage. So therefore current equals power divided by voltage. So the power is already in watts for us, so we don't need to convert it from kilowatts, which is sometimes what they make us do to try to catch us out. And that's divided by 230 volts, so that's 4.4 amps. It is advisable to use all 230 volt power tools with a residual current circuit breaker. We've talked about them before. How does an RCCB operate? How does a circuit breaker operate? So remember, you've got with any kind of device, right? Look, if that's the mains there, right? You've got the live wire, which takes the current into the appliance. So in this case, it's the drill. Then we've got the neutral wire, which takes the current away. What the circuit breaker does is it compares how much current's going in with how much current's coming out. If it's the same amount of current going in and out, then everything's fine. But if there's less current coming out than has gone in, something's not right, and it'll break the circuit. So the circuit breaker compares the current in the live and neutral wires and switches off the circuit if there is a difference. Figure 1 shows the current potential difference graph for 3 wires, A, B and C. There's the current going up the side, there's the voltage going along the bottom. Using figure 1, how can you tell that the temperature of each wire is constant? Well, that's because each line is a straight line. Ohm's law says that the current will be proportional to the voltage as long as the temperature remains constant. So if the temperature is constant, then we'll have a straight line. Obeys Ohm's law. Which one of the wires, A, B or C, has the greatest resistance? Write the correct answer in your box and give a reason. So remember, Ohm's law, voltage equals current times by resistance. So therefore, resistance equals voltage over current. Now, for each size of voltage, that one and that one, C has only got a small current. So if this current here is little, so they're all got the same voltages, but if the current is littler, that makes the resistance get bigger. So C has got the biggest resistance. When I teach this, what I say is the flatter the slope, the bigger the resistance. So as the gradient gets less, the resistance gets bigger. So the correct one is C. Give a reason for your answer. It has the smallest current for any given value of voltage. Remember, we use resistance to control the size of the current. If you've got a big resistance, it only lets a little current come through. Look at A here. Look at the size of the current. It's massive, big current. So that must just be a little resistance because it's allowing a big current to flow. A student measured the resistance of 4 wires. Table 1 shows the resistance of and other data about each of the 4 wires, J, K, L and M. So it tells you the type of metal it's made from, the length, the diameter, so that means how wide it is, and the resistance in something or other. So that's length in centimetres, that's diameter in millimetres, that'll probably be resistance in ohms. They're looking for the units. The last column of table 1 should include the unit of resistance. Yeah, what is the unit of resistance? It's ohms, named after George Ohm. The resistance of a wire depends on many factors. Look at table 1. Which two wires from J, K, L and M show that the resistance of a wire depends on the length of the wire? So which two wires? So remember, if you're going to compare something, it's only the one thing that you're trying to compare that has to change. So we're looking for a wire that depends on the length. So everything else should be the same. So the wire should be the same type of metal. So we can rule out M straight away. And it needs to be the same. It needs to have a different length because that's what we're trying to compare. And the diameter needs to be the same. So there we go. That's the same. That's the same. And the length is different. So the only thing that's different is the thing that we're trying to see if it makes a difference. So wires K and L. They are the same type of wire and have the same diameter. They only vary in their length. So in other words, all other variables that could affect the resistance have been kept the same. A student looked at the data in table 1 and wrote this conclusion. The resistance of a wire depends on the type of metal from which the wire is made. The student could not be certain that her conclusion is true for all types of metal. Suggest what data is needed for the student to be more certain that the conclusion is correct. Should need to test more types of metal. The resistance of a wire can be calculated using the readings from an ammeter and a voltmeter. Complete figure 2 by drawing a voltmeter in the correct position in the circuit. Use the correct symbol for a voltmeter. So a voltmeter always needs to go in parallel over the thing you're trying to measure, and it's simply a V inside a circle. That's a voltmeter. In a circuit diagram, a wire can be represented by the symbol for a resistor. In the box below, draw the circuit symbol for a resistor. Easy peasy. It's just a box. Just like that, with a couple of wires coming out the either end. A 12 volt filament bulb is connected to a 12 volt power supply. Figure 6 shows how the current changes after the bulb is switched on. So these are time in seconds, so these are very, very short amount of time. So when you very first turn it on, the bulb, the current goes up very fast, and then very quickly it stabilizes to a certain current. After 0.1 seconds, the bulb works at its normal brightness. 0.1 seconds, that's there. What is the current through the bulb when it's working at normal brightness? So from 0.1, just come across this way. And that's 1, that's 1.5, that's 2 each, and there's 5 boxes, then each box is 0.1, so that's 1.7 amps. Bulb works at normal brightness for 30 seconds before it is switched off. Calculate the charge that flows through the bulb in the 30 seconds before it's switched off. So in other words, you can forget about that silly part at the beginning. Give the unit. So calculate the charge, so we're looking for Q. So Q equals our target. Time is 30 seconds. And we know that the current at normal operation is 1.7. So charge equals current times by time. That's an easy equation to remember. When you're charging your mobile phone, you've got to plug it into the mains, so a certain amount of current flows through your battery into your phone, and you leave it plugged in for a certain amount of time. The more time that you leave it plugged in for, and the mains will supply a large current, then that means you'll get a big charge. And the time does need to be in seconds. So if it said it was in minutes, remember to convert it into seconds. And that'll be 51, and the units of charge are coulombs. I'll write that down just in case you don't know how to spell it. Next bit, calculate the energy transferred by the 12 volt bulb, so that's our voltage, when it is working at normal brightness. So we know that the current was 1.7 for the 30 seconds. Okay, so energy is our target. Now remember, EastEnders equals the Queen Vic. Now we've just looked, this is part 3, so it obviously goes with a part 2 and part 1. So we've just worked out that the charge was 51 coulombs. So 51 coulombs times by 12 volts is 612 joules worth of energy. Between 0.02 seconds and 0.08 seconds there is an increase in both the resistance and the temperature of the filament metal inside the bulb. Explain in terms of the electrons and ions inside the filament why both the temperature and the resistance increases. Well, if we look back at the graph, we can see that the current between 0.02 and 0.08, the current is coming down. But before that, the current had went up. Now, if the current had went up, that means it's going to get hot. Now, as it gets hot, the little atoms inside the wire, or the little ions inside the wire, are going to start to vibrate more. That'll increase the number of collisions between the electrons and the ions. So explain in terms of the electrons and ions inside the filament why both the temperature and the resistance increase. As current increases, the temperature increases. So atomic vibrations, or ions, atomic vibrations increase. So collisions between ions or atoms inside the wire and electrons moving through the wire increase. So in terms of electrons and ions inside the wire, explain why both the temperature and the resistance increases. So as the current increases, the temperature increases. So atomic vibrations increases. So collisions between the ions and atoms inside the wire and electrons moving through the wire increases, which makes the resistance increase. Now that is very, very waffly, and it might be difficult for you to remember. So what if I write it like this? As temperature increases, atomic vibrations increase. Now what I mean by atomic vibrations is inside the wire you've got all the little atoms, but when it's a metal we don't call them atoms, we call them ions, because they've all lost electrons to become charged. So if they've got more temperature, they've got more energy, and if they've got more energy, they're going to start to vibrate more. Now the poor little electrons that are trying to make their way through the wire, all of these ions inside the wire are all vibrating now. So it's like you trying to walk down a corridor and nobody in the corridor is standing still, they're all moving about. Well, they're going to bump into you more. And all that resistance is it is collisions between the electrons trying to go down through the wire, in other words the current, and the ions that make up the wire. So as the temperature increases, the atomic vibrations increase, so the number of collisions increase, so the resistance increases. Now that is actually an answer for A level as well. That would be a relevant answer right the way up to A level physics. So I hope the little picture and the explanation is helpful. And that's how to take care of business. Good luck with your paper too. Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained. Thanks very much and bye for now.